Alright, I thought I'd just make a quick video series on equilibrium balance and levers. I'm going to divide this into three quick videos that should hopefully give you some more insights on the method of solving these kinds of problems. So since we're dealing with equilibrium, there's two kinds. We can typically deal with dynamic equilibrium or static equilibrium. The scenarios that you guys will be working with deal with static equilibrium situations only. In other words, what kind of forces are required for the system to not move and therefore remain stationary. Right? It's not going to there's not going to be any kind of rotation, and there's no translation. So uh, yes, static equilibrium is what be dealing with for now. In terms of levers, you guys should know by now that there's three classes of levers. You've got your class 1, class 2, and class 3. Um, they've each got their advantages and disadvantages, and the point would be to try and like unpack what would cause a particular lever system to have an advantage or a disadvantage, which means you have to unpack the mechanical advantage of the system. In other words, is that particular system favoring the resistance force or the muscular force? Alright, so let's start unpacking this scenario over here. So the head and neck system is going to have a center of mass, right, which is being pulled downwards by gravity. It's going to be pivoting about a specific point, and in terms of the head, it tends to pivot about your atlantoaxial joint, right? So that's where I'll draw the fulcrum, and in order to keep this stationary, we need some kind of a muscular force. And what I'll be drawing over here is the splenius capitis muscle, right? It's going to be exerting a downwards force. Because if this head was pivoting about this point, it would rotate that way, right? You can use the right hand rule in order to denote which way it's going to rotate. And in any case, the splenius capitis muscle inserts over here at your mastoid process and originates in your upper thoracic vertebra. Alright, so um, there's a few things that we have to continue to unpack over here. First of all, since we're dealing with forces relative to some axis of rotation, I'll just continue drawing a straight line. Remember that when we deal with forces and relative to an axis of rotation, we typically deal with torques. So the torque of a particular system is equal to a force that would be causing a rotation multiplied by the distance that that force is from the axis of rotation, specifically the perpendicular distance of that force to the axis of rotation. And that's in essence what I'm just kind of trying to draw down here. I'm just extending the straight line of this particular force, and then the perpendicular distance of that force to the axis of rotation is just what I'm drawing in over here. So that's at 90 degrees to that force. And we'll call that D1, right? The force that we're dealing with in the system, like I said, it's the center of mass, or the center of gravity of the head and neck object. So I'll just call that the force of the head, right? To balance that out, I need this muscular force over here. I'll just call that Fm. And remember, it's the perpendicular distance. If I want to try and find the torque of the muscle, it's the force of the muscle multiplied by its perpendicular distance. I'll call that D2. And that would be over here. So I'll just draw that in, and that's the perpendicular distance over there to the force, or from the force to the axis of rotation, from the axis of rotation to the force. My apologies. So what do we need in order to have static equilibrium? Well, we need to kind of figure out which way each of these forces is causing a rotation. If I look at this FH, it's on the left hand side of this fulcrum, and if again use the right hand rule in order to dictate the direction of rotation, I've already denoted up here that it would be rotating anti-clockwise. Now remember that our convention is set up this way, that anything along the y-axis going upwards, anything on the x-axis going to the right, and anything causing an anti-clockwise rotation is denoted with a positive sign. So in this case, the torque of the head is equal to the force which we've causing that rotation, which is the center of gravity, multiplied by that perpendicular distance, which we said was d1, and that's going to be ascribed a positive value, right? So we'll call this the sum of the anti-clockwise moments, or the anti-clockwise rotations. That has to equal the sum of all the clockwise rotations, right? In other words, the clockwise rotations, if the anti-clockwise rotations equal the clockwise rotations, then the system will not have a net rotation and would therefore remain stationary. Now the clockwise rotations would be this muscular force. Remember, it's a certain distance from this axis of rotation pointing down, and if I again use my right hand rule to solve that, it would cause a rotation in the clockwise direction. So the torque of the muscle, which I've already got up here, is the force of the muscle multiplied by d2, where d2 is that perpendicular distance over there. So there's one or two more things that I need to know. First of all, the body mass of this individual is 70 kilograms. The weight of the head and neck is equal to, in essence, 7.2 or 7.3% of the total body mass. So it's 0.073 times, I'll put body weight in here since we're trying to find the weight of the head and neck. I'll give you guys d1. In other words, the distance that the center of gravity of the head is from this axis of rotation is 8 centimeters. The distance that the muscle is from the axis of rotation is 5 centimeters. And therefore the question is, what is Fm? And what is the mechanical advantage of the system, right? Okay, so if I equate these aspects to each other, I have to solve for a few things first. The first thing I have to try and do is find out what this FH is. Now FH is the, in essence, weight of the head and neck, and that's what I'm trying to solve over here. So that's 0.073 times body weight, right? So FH is equal to 0.073 times body weight, which is going to be equal to body mass multiplied by gravity. So it's going to be 70 times 9.81, right? And that is equal to 50.13 newtons. Alright. Therefore, the torque created by that FH is equal to FH times D1, which is 50.13 newtons multiplied by 8 centimeters, but remember it has to be converted to meters. So 8 centimeters multiplied by 1 meter per 100 centimeters. Remember, there's 100 centimeters per meter. That means the centimeters cancel, and I'm left with 8 divided by 100, which should be 0.08. So all of this equates to 0.08 meters. Okay, so 50.13 times 0.08 is going to give me 4.01 Newton meters. Okay, Fm is what I'm trying to solve, and we said that the sum of anticlockwise moments must equal the sum of all the clockwise moments. So I've got 4.01 Newton meters must equal this Fm multiplied by d2. So if I make Fm the subject of the formula, Fm is equal to, and let's just change the colors over here again, 4.01 divided by d2, which we've already got over here, is 5 centimeters. Let me just solve that for you here. d2 is 5 centimeters multiplied by 1 meter per 100 centimeters. So again, if I've got 5 divided by 100, it is 0.05 meters. So if I divide that by 0.05 meters, I sit with, let me leave it in red, 80.2 newtons. Okay, so I've solved for this, the muscular force. I want to find out what the mechanical advantage of the system is. Now remember, by definition, mechanical advantage refers to the force moment arm divided by the resistance moment arm. Now the force moment arm we said was 0.05 meters. The resistance moment arm was 8 centimeters, or 0.08 meters. So I'm left with 0.625. Now, for a system to have a mechanical advantage, this ratio should be greater than 1. So what we see here is that the ratio is definitely not less than or equal to, is definitely less than 1.0. Therefore, the mechanical advantage of the system tends to favor the resistance force, right? So in other words, you have to produce more force than what the resistance is, right? So it puts the muscle at a disadvantage, and it's primarily due to the ratios of these moment arms. We can see that the weight of the head was only 50.13 newtons, but my muscle had to produce 80.2 newtons in order to keep the system in equilibrium, right? So the mechanical advantage is definitely in favor of the resistance. Alright, so that's how you solve part 1. I'll leave it there for now, and I'll see you guys in part 2.